Let's talk about controls. When we're talking about controls, we're talking about control systems in particular, and most of these are focused on the automatic control of process variables in some kind of system. And often they are mechanical systems where we're controlling the position of an actuator or the position of a tool or something like that in a mechanical manufacturing process, for example. They might be electrical controls where we're trying to create a specific voltage under varying conditions. We might be doing something like fluid control, making sure that we're keeping a certain amount of pressure or amount of flow in a system. Chemical controls are very common where we're trying to make sure that a reaction is happening at a particular rate or a process is occurring, some chemical process is occurring, a temperature is being maintained, all kinds of stuff like that. There's even such a thing as financial controls, as like putting more money in or taking more money out as the stock market changes to maintain a certain level of return on a set of investments or anything like that. We can even have biological control systems that monitor biological reactions or biological systems like culturing bacteria or for the generation of pharmaceuticals or all kinds of different things. There's a couple of main types of controller designs. The first kind is open loop controllers, and these are control designs that have no feedback. We're not sensing the position or anything about the system itself. We are just sending a signal and hoping for the best. The types of things that are like this are our motor controller without using the encoder sensors, where if we're not using the encoders, we are just hoping that we're reaching some speed. And typically we just set it and forget it and hope for the best. These are things that don't give us an actual feedback on whether or not we've reached the goal of whatever variable we're trying to control in the system. Closed loop controllers, however, do have feedback. In this case, we have our input, which is whatever our control signal is, being fed to the plant, which is the system that we're controlling, and that could be a mechanical system, it could be an electrical system, it could be the motors on our robot. Then that generates some kind of output that we are then measuring using a sensor that gives us information about how close we are, and based on that information we can create a new control signal that gets fed back into the plant, and this closed loop makes the system control better, right? Here's two examples of open loop and closed loop control, and both of these we're trying to control the position of the end of this pendulum. So on the open loop side, we just move the base of the pendulum to our target area and see what our error is, right? We want to minimize the angle of the arm, but we don't know that we can't measure anything, so we just move it to our 0.5 position and hope it gets there and it's okay. However, in the closed loop part, we have very tight controls where we're observing the angle of the pendulum, and we can modify the speed of the carriage so that it ends up in the location much faster than if we had an open loop control. And this gives us a lot of precision control over a system that has a lot of unknown dynamics. So the most basic controller that is closed loop is an on-off controller. And you can kind of think of these are super common because you'll see them in thermostats and heating, ventilation, and air conditioning units. And basically a bang controller or an on-off controller says we only, rather than having levels of control, like we can control the speed or intensity of the fan, we just have it's either on all the way or it's off all the way. And that's why it's a bang controller, because we have no finesse in here. Let's look at an example in a simulated thermostat environment. So this is our thermostat environment, and you can see it's Phoenix in the middle of the summer, and because our control is 0 at this point, we have no control and the room just gets hotter and hotter and hotter, right? So let's write a controller for this configuration. So what we have as inputs to our controller are the temperature and the previous last state. And we're just going to go with a real simple controller that says if the temperature is greater than our targ temp, then I want to return true. That turns on the air conditioning system. Return false, right? Very straightforward. So let's run this and see what happens. So here we go. We are keeping at a very steady 72 degrees, and we've got just a little bit of fluctuation in here, but you can see that our controller is switching very, very quickly between on and off. This is a really, really big problem, because if my AC is switching on and off, that's putting a lot, is switching on and off very, very quickly. That's putting a lot of load on my air conditioning system. The most strain comes from when the system turns on from an off state. It takes a whole bunch of current to get the fan moving, the compressor has to spin up, all that kind of stuff. So my AC will burn out very, very quickly if I don't do something about it. So now we've made some modifications to our controller to incorporate a delay, and your actual home thermostat does this. If you watch it after it changes, it'll put in a wait cycle before it does one change or another. So in this case, I've got an external counter, and I have it incrementing every time the controller counts. As long as that count is less than 50, it's not going to do anything. It's just going to do whatever it was doing before. Once it is greater than 50, once that delay time has passed, it resets the counter and then decides whether to turn it on and off. So let's see what happens in our room now. So here we are in our room. We can see that it's bouncing. Looks like it's bouncing between about 85 degrees and about 60 degrees. So this one is not doing a great job of keeping the room at a cool, even temperature. So what we can do is we can actually just make this a little bit shorter, and this defines sort of the thrashing. If these are by minute, 10 minutes on, 10 minutes off, 10 minutes on, 10 minutes off, doesn't really matter that much. And we can see there's a little bit of fluctuation here, but we're keeping it much more even. If we try to increase the set temperature, we can set that and let it rise a little bit higher. We saw that it rose up, and now our average set temperature is a little bit higher. If we drop our set temperature, then we can see that it cools down and it stays in that level. So this is a bang bang controller. It's only going on and off. And the big deal here is that to get really smooth behavior out of a bang bang controller, you have to have it switch on and off really, really quickly. And that's kind of what the motor control system is doing on our robot. We're getting fine speed control of the motor by using PWM, which is switching the motor on and off very, very quickly. We can't do that with an AC system, so we have to have some delays in there, and that introduces error in the ultimate process variable.